speaker, the last in a row, is Professor Martin Glicksman. Martin is professor at the Florida Institute of Technology in Gainesville and a member of the U.S. National Academy of Engineering. Martin has made original contributions to certification. Especially famous is his research on dendrites and metallurgy of microgravity experiments, where he analyzed with high precision almost the stability of growth morphologies. He is also author of several well-received books. Marty, I invite you to give the talk on future control of cast microstructures. Please.
Thank Professor Fan for inviting my participation in this very interesting forum. This morning's talks have been extremely interesting about the production of ferrous and non-ferrous materials. I'm going to sort of shift to a little more basic look, how perhaps basic metallurgy might have some influence on our future. So I called it a look back and then think ahead. And I wanted to take one example at least of a very basic solidification development that truly became a very important development in metallurgy in general, affecting a number of major industries. And I consider it to be, I think you will too, a major success of how casting can truly improve society. So the future is an interesting topic. I'm not a futurist particularly, but when Professor Fan said, let's talk about the future, I wanted to see what other people had to say. So here's a rather famous American quote. It's tough to make predictions, especially about the future. And that's a typical remark from Yogi Berra. But there's a more thoughtful and perhaps uplifting concept, and a rather famous one. And the future is unknowable, but the past should give us hope. I think that's a very uplifting statement by Sir Winston Churchill. And I did some checking since I'm here in England, and I noticed he's on the obverse side of your 5-pound note. And I guess the Chancellor of the Exchequer picked out a quote to put on the bill. You probably can't read it, but I didn't want to use that because it's the famous blood, sweat, tears, and toil. So we'll use the bottom quote as our uplifting concept from Winston Churchill. I'm going to break the talk into two parts. The first part, I want to show you some innovation in casting technology that truly shaped not only metallurgical technology, but very important industrial sectors in our country. So this is our look back. And what I chose today was directional solidification, and so-called DS actually led to more than 6 decades of worldwide aircraft development, and more recently, the presence of huge land-based turboelectric generators. And without this particular development, this would not have happened. This development was considered so significant that ASM, from their Materials Achievement Award, and this is impressive, it designated DS as one of the 50 greatest advancements in metallurgical history. And that is quite a kudo for such a development. Even the American Society for Mechanical Engineers used a landmark engineering invention, and there aren't too many of them, saying that DS does 3 things. It improves jet engine efficiency, it lowers emission, and extends the interval between engine repairs. If you think about it, those are the 3 key elements of an aircraft engine that makes it commercially viable and societally acceptable. So I thought I'd spend a few more minutes explaining how DS really entered our industrial sectors and literally earned billions for the developers. So I chose the Pratt & Whitney so-called 10-year miracle. And that designation actually came from Professor Chandrasekhar from the NIAS in Bangalore. Professor Chandrasekhar studies technology and the impact on society and the military. He's written extensively on these subjects. So this is his designation as the 10-year R&D miracle. This started off with a very basic discovery by Frank Verschneider, and it was done at the GE Steam Turbine Division. And in a nutshell, this DS, as developed by Frank Verschneider, provides grain boundary orientation control in complex castings. That's what it does. And I think it was considered the perfect discovery at the perfect time. One problem, it was not at the perfect place. And in fact, GE was unfortunately unimpressed by Verschneider's development. Verschneider was very discouraged, and it took very little, I think, encouragement from a fellow by the name of Bud Shank to attract Frank Verschneider and say, why not join Pratt & Whitney's Advanced Materials R&D Laboratory, and you'll be able to pursue R&D for jet engine metallurgical development. And Frank left GE and went over to Pratt & Whitney in Connecticut. Well, Shank put him together with a core of really first-class metallurgists. I've put the names of the top 6 people. A couple will come up in a minute. These 6 began the serious development of DS control, which is a macroscopic solidification control, and basically teamed this core group of metallurgists and expanded it ultimately to 200 engineers and technicians. So you can see this was a very serious attempt by Pratt & Whitney that recognized that's what's going on here, although it was a very basic discovery, had very important implications for them. And as you'll see, it took about 7 years for this team ultimately to produce the patents that Pratt & Whitney needed for directionally solidified, aligned, and eventually single crystal turbine blades. Now, technical success didn't occur for 10 years. I think that's where Professor Chandrasekhar's 10-year miracle comes in. It took 10 years for technical success, and I stress the term technical. Turns out, at the time, actually a few years previously, the Lockheed Skunk Works, very famous American think tank for aircraft, came up with the SR-71, which was the first hypersonic reconnaissance airplane. The problem was the engines it was a Mach 3 plus plane. The problem was the operating time for those jet engines was somewhere around 30 to 40 hours. Then the engine had to be taken down, removed, replaced. This was obviously unacceptable because of the operational necessities of the Blackbird. However, Lockheed was producing 1 Blackbird per year. And for Pratt & Whitney, that did not exactly look like a hopeful way to get a return on your investment of some 7 or 8 years with a huge team of personnel involved. Well, of course, they saw that the directionally solidified engines gave many, many multiples of some 40 or 50 hours of operating time, and the success was demonstrated beautifully in the Blackbird. They were very lucky because just about at the same time, Boeing came out with the 747. And while they didn't invite Pratt & Whitney in immediately, again, it was a very new concept in this engine, when they started seeing TBO, that's time between overhaul, approaching 30,000 hours, it's now about 45,000 hours. That's 5 years of running the engine. That proved the commercial success, and coincidentally, the 1574th 747 was delivered, I think, to Europe at the beginning of this year, and the production line is shut down. So that's the end of the jumbo jets. But when you think about it, this engine probably earned for Pratt & Whitney over that period many billions of dollars. I think many of you have seen these pictures, but in case you haven't, I thought I'd just quickly show you how this basic discovery quickly moved along. On the right, you'll see the polycrystalline blade, lots of transverse boundaries through the stress axis, leading to, of course, early fatigue and stress rupture at these high temperatures. These blades operate somewhere around 25,000 Gs. The middle group of blades, oops, what happened here? I think I'm in trouble here. What happened? Yeah, okay, we'll get back there. There we go. I didn't use the right pointer. This middle blade is the Versnyder aligned DS. That's still available today. It gives fairly good performance, but to reach the ultimate single crystal form required yet another invention, very basic idea, done by two of the metallurgists, Tony Germain and Barry Piercy. And Piercy had an observation that when the grains from the tang area of the casting make a right-angle bend, there's a significant reduction in the grain density. And Tony Germain said, well, if that right-angle bend reduces the number, what do you say we make a continuous change of solidification direction using a thing called it's a one-turn helix called the pigtail selector. And then the pigtail goes into the blade mold, and this device, which is patented in 1971, gives better than 95% single crystallinity to the blades. So today, this has become a rather specialized and sophisticated form of solidification. Alcoa bought Howmet, which was active in the area back in 2020, and has continuously invested in improving the foundries. Here's just a quick glimpse inside the Hampton, Virginia Howmet that makes the directionally solidified blades. In fact, you can see a number of these lost wax ceramic castings being directionally solidified on a turntable here. You have choices now of DS aligned, which are fairly expensive. In the, I would say, approved and tested form, these blades run about $12,000 each. And you can, of course, go from DS aligned to single crystal. They're even more expensive. And then for very special applications, I haven't been able to find out exactly where they do it. They have the airfoil design of the blade gets into some difficult vibrational modes. And to eliminate that, you can change the elastic moduli by changing the crystallographic orientation. So they have this thing called prescribed orientation, and they will custom make blades of that orientation. At the very bottom, I just listed all the users. These are all the turbine users around the world. they go to Alcoa Howmet to supply most of these DS blades. So it's quite a business. I did want to mention that GE, though I'm sure they regretted their original discouragement of Frankfurt Schneider, GE ultimately, of course, makes their own airplane engines for jets. But more importantly, in 2003, they came out with the 9H combined cycle 530 megawatt turboelectric generators. So this now is a whole new area, and those generators use blades up to a half-meter long, single crystal blades over a half-meter, weighing over 100 pounds. So that's what that kind of basic discovery ultimately did. Let's move on now. I wanted to mention a couple of recent things that we've worked on that I think are solidification phenomena that are not really well recognized yet, and I think may affect things in the future, the far future. But as I showed you, that's what happens. We'll talk first a little bit about observations, because there's been arguments in the field about what's noise-driven and what is deterministic. Another thing, the interface modeling has proved to be absolutely essential in what I'm going to show you. And we can examine some new mesoscopic features that are not even thought about in terms of control. And what I want to show you today, because I certainly got a big kick out of it, and as it worked, we combined what I'll call oh my heavens. There's a button here that confuses me a little bit. We can combine variational theory with phase field models, and we can use what we call geometric homology to learn some very new interesting things about solidification. And I'll demonstrate that. Okay. Let me take a moment to show you how I think modern solidification theory sort of evolved. I'd say before 1950 we knew almost nothing about solid-liquid interfaces and the kinds of structures that form there. But it was Bruce Chalmers and his Canadian students who back in the mid to late 50s began to use techniques of pulling the solid-liquid interface away from the melt and looking at structures that no one knew existed. I call those ex situ solid-liquid structures, and people began to realize there's a lot going on at that interface besides what you might see as ice freezes and so on. So moving on to the 60s, theories came in to start explaining those structures, and probably the most prominent of those is linear morphological stability, which came out in 1963. That was Mullins and Sekirka, and in Russia, Voronkov came out with the idea that noise is present, and the noise gets amplified, producing these structures. Also, Chalmers' book, Principles of Solidification, came out in 1964, and I think in many people's opinion sort of set the stage for what we call modern solidification science, and really codified many ideas that hold true today. Another important development was by one of Chalmers' students, Ken Jackson, who passed rather recently. His so-called alpha factor, which is the ratio of the entropy of fusion to the gas constant, he proved correlates morphology and thermodynamics. That if that alpha factor is 2 or less, that's typical of the metals, you get rather metallic solidification, and as it goes up to numbers above 2, up to maybe 50, 60, you get needle-like and spherulites, rather non-metallic solidification. In work that I published with Bob Schaefer back in 1970, we finally did what we call in situ observation. And I just pulled these out to show you why these observations did not really coordinate with linear morphological stability. So we're looking through a transparent melt, and we picked the substance through the Jackson alpha factor. This happens to be a body-centered cubic material, but it's got a transparent melt, and we're looking down at the plan view of a solid-liquid interface with 3 grains intersecting with a grain boundary groove. And that groove is about 20 microns wide. And as the solidification front advances toward you, I circled the fact that you suddenly see 3 so-called pre-dendritic discs. And those discs actually lead to the breakdown of the furrow that builds up out of these linear grain boundary grooves. And what happens is it kicks off an instability in the other direction, and you can see them developing as adjacent helix. 3 minutes? Okay. So, just moving on, the interfacial studies, these were Green's functions done by John Long Grubb at UC Irvine for us, showed the reproducibility of these structures. This was a low noise analyzer, and if you took the anisotropy away, which is typical of metals, we noticed that there was extreme pattern sensitivity. And you can see now that this initial blob with develops into a sort of organic-looking leafy thing, and that began to tell us that the input has some feature which winds up driving the pattern. And we call this capillary-driven pattern formation. Geometric homology is just comparing 2 identical profiles. The variational ones are ordinary differential equations, and the right-hand ones are partial differential equations. They're solved numerically over time, whereas the others just emerge instantly from the equations. And I won't bother reading these differences, but basically on the left they're exact thin interfaces. On the right they're diffuse interfaces that evolve over time. Let me show you the results. You compare them and you can see what happens. So here's the new work I wanted to tell you about. This was just published at the end of last year with my colleagues Wu and Ankit from Arizona. You start off with the equation of the interface, and it emerges immediately into basically the shape of the solid-liquid interface. On the phase field model, you run numerics, and you start off with initial state. First, you've got to prove it is stable, and that quickly develops into essentially a comparable interfacial shape. This yellow curve shows the comparison of adjusting the parameters to fit the evolved shape. Here's the difference, though, and this is the critical point of the whole exercise. You calculate from field theory everything exactly: the chemical potential, the gradients of the chemical potential, the fluxes that are traveling through the interface under those gradients, which result in either heating or cooling, as I'll show you. From this identical counterpart, we go ahead and measure using essentially post measurements. You actually measure the chemical potential very accurately on the interface. And finally, here's the results. The surface Laplacian, which is what we calculate from the variational ones, give essentially almost exact fits to the measurements our measurements. What's very interesting, those blue areas is where cooling is occurring. This is a stationary interface. And what these results are telling us is there is a mechanism of thermal transport, I think it's a form of thermal diffusion, that goes on in castings that we're not particularly aware of. And just to check it, look at the vector map of the heat flowing near these boundaries. And we have simply a macro gradient, which should give us perfectly straight vectors. You can see that these thermodiffusion effects actually suck the heat in near these boundaries. To check, final slide, to check to see whether the thickness of the interface is allowing more or less of the currents to flow along it, we measured the cooling rate as these residual potentials as a function of the thickness of the interface, and indeed it's a linear result. So, here's my conclusion. Please remember the pathways followed toward the future aren't direct. And I'll use one more American quotation. The future ain't what it used to be. And thank you.
Thank you, Marty, for this inspiring talk. There are certainly questions about it. Okay?
Marty, just quickly, was that in a pure material or?
Yes, that was a one-component material just to make if it was an alloy, you would have a comparable current of
compositional flow as well, which would be interacting with that, presumably in an alloy.
Right, thermodiffusion of the solid.
Yeah.
In this case, it was thermodiffusion just of a heat current. And it checks out, it's there.
It's absolutely fascinating.
Yes, and we're unaware of it.
No, I learned something. It's fantastic. I like it.
Thank you.
Another question?
Okay.
Is this heat flow you calculate for the interface energies, is this something which might change the microstructures, dramatically?
I would not say dramatically. It turns out, and this is a fascinating point, phase field generates the structure with these fluxes flowing, whereas the variational theory is just an extremal picture, is zero thickness interface, there's no fluxes. I am convinced, the next step I think in this research would be to check the deviations from the phase field shape to the variational shape. And indeed, I'm convinced there will be a small correction due to this additional cooling at the interface. We can see it very beautifully in the isotherms, and therefore the interface should change a bit. My question is, can you think of casting processes in the future where since these are deterministic currents, you can calculate them, therefore you can interact with them. You might be able to apply magnetic fields. Now the Chinese are doing that. They're putting fields on up to 12, 13 Tesla. And they're finding out that the surface energy and these are in metals, between the solid and the liquid is going up with the static magnetic fields. That means all these effects go up proportionately. Mm-hmm. In addition to magnetic fields, pressure should affect them as well. Mm-hmm. So you can interact with these things deterministically.
Okay.
Can I just check, as calculated, the thermal flow is going on to maintain a stable interface shape. It's not changing. There's no evolution of shape. That's a static shape, I think you said. And it's being maintained under the thermal flow.
Right. That static shape has a certain curvature gradient or chemical potential gradient, which is demanding that flux flow.
That's what I took.
So it's part and parcel of the local equilibrium. Now, those are please remember, those are not equilibrium pictures. When you hold an interface like that stationary, you're generating entropy. So we're not violating anything. But the whole system then is being exposed. And I must say, the new multi-phase field calculations done by my colleagues at Arizona, it's just wonderful to be able to see that and how the heat flow is diverted.
Okay, thank you very much.